Our next presenter is Amar Ajanova, representing an ion source project as a seed to build capacity for next generation accelerator physics in Bosnia and Herzegovina.
Yeah. Hi, everyone. First of all, thank you to the organizers, especially Jutta, for allowing us young scientists to be here today and talk about and learn from distinguished scientists in the field. My name is Amar Janowicz, and today I'll be talking about a seed that actually developed some odd 5 years ago when I was just a summer student at CERN. And then professors at our University of Sarajevo really grabbed the project and allowed it to take off in the time while I was doing my PhD. So I'm going to talk about, this Sarajevo Ion Accelerator project as a seed to build capacity for training future accelerator physicists. So what is this project? Really, it's a collaboration between an academic institution, which is University of Sarajevo, a scientific institute such as CERN, GSI, and Jožef Stefan Institute, and a couple of industrial partners, which are COSILAB and Pantechnic. It was supported by the Three Physicists Foundation and our ministry in Bosnia and Herzegovina of Education and Science. And my journey, so we're really taking this project in building the capacity of training future accelerator physicists from scratch and step by step. And really, so what it started with for me was in January at JUAS course, which was probably the most intense period of my life after doing PhD. But I would do it all over again, and I would suggest it to everyone who's an aspiring accelerator physicist, because I see a lot of young people in the crowd to do it. And then in April, we started with a small international atomic agency project to develop radiation shielding calculations. And then I worked with some of our developers for the control system for the accelerator that we're planning to build. And finally, in August, we started the tests at CERN. And so this is the lab plans of our University of Sarajevo facility. You can see it's quite a large space. You've got 12 meters by 6 meters. And the focus of our research at CERN is just a test stand with the ion source and low energy beam transfer line. So we're focusing our technology, our configuration really on two main principles. One is based on the spectrometer, which is just magnetic dipole here, and the other one is based on the Wien filter. And I'm not going to take too long to describe the results, but we managed to obtain, both Alessandra and I managed to obtain to distinguish between the mix of helium-2 plus and helium-1 plus beam in both phase space and the spatial coordinates. And this is one of the results that took me a month to do, but now it will probably take me half an hour, which is getting the beam and simulating it matching it to the RFQ plane. And we're able to do that now. But of course, when we start the experiments, when the ion source arrives, it will be anything but this. And while we're growing with this, we're trying to allow for students to grow with us. And I'm very proud to present 3 student projects that developed this summer at CERN in Dalis, Naida, and Medina. Thank you.
Yeah. I just have to compute it to the first slide.
Hello, everyone. My name is Danis Pradaric, and this summer I worked with Aris on the extraction system he just showed before, and I'm here to present a few beam dynamics results from the simulations. So the goal of the study I was doing with Aris during my summer internship at CERN is to test the AM01 extraction system, which integrates beam extraction, acceleration, and matching to the lineup for RFQ, as he mentioned before, in a way that we need to generate as many different types of beams, because it is not possible to accurately simulate the extracted beam from the plasma source and then see how the beam evolution behaves with different different beams. So the goal was to stress test the system to see how, like, to have some results that can serve as a reference point to experimental results that are going to come soon, I hope. So the tools and software that I used were, of course, Travel for the numerical simulations of the beam dynamics, and also one additional thing, which is called PyTravel. It's a set of functions written in Python that can be used as a tool to help and ease the simulations with Travel. Okay, so about system, Aris already mentioned most of this stuff. So this is just the model on the right side. On the left side, you have some specifications of the system already mentioned before, so I'm just going to continue. Okay, so the beamline used for the simulations was as follows. We tried to simulate the source conditions the best that we could to have an idea how the system is going to behave in real life. So the main thing we focused on was the transmission of the beam to the RFQ. So from the extraction point to the system and to the RFQ, just to see how the beam behaves through the system itself. And here are some characteristics of the system we found out during the course of this study. Is the system demonstrates effective focusing capabilities, and you can see that on the first plot on the left with the RMS beam size in reference to the position of the beam in the system, because the system itself is just 2 centimeters in length, and you can see there how it looks like. And another thing that was really important was that no particle loss is observed in the system for the current configuration. So, and this can be seen in the second plot, the transmission position plot. The only drop off in transmission is at the end, which is due to the mismatch with the RFQ acceptance plane, and it's not that big. So the energy gain was as expected for any beam that we tested. It was 45 kV. The different beam distributions that were tested in the system were a Gaussian distribution and the uniform distribution. And the main thing we could show is that the uniform distributions tend to have a higher transmission for similar parameters of the beam. And here on the graphs below, we can see how the beam looks when accepted to the RFQ. Also, another study that we done is to see for which parameters the beam will have the highest transmission through the systems. Firstly, it was the energy values, so the beam energy, and we can see for lower beam energies, around 10-20 eV, we have the highest transmission, which is okay because that's the most mostly comparable to the source itself. And then we did also simulation with a range of emittance and alpha parameter values to see if there's an optimal set of parameters for the configuration. And these are the results of the simulations on the shown in figure 2. So there's a big area of set of parameters that have high transmission above 95%, all the like light yellow green color. So this was also some good results. And in the end, the conclusion is everything I mentioned so far. The system effectively focuses the beam while accelerating it to desired energies, and it maintains high transmission of the beam to the RFQ. Uniformly distributed beams achieve higher transmission values, and higher transmission is achieved with lower input energy distributions. This approach is more compatible with the beam energy extracted from the source itself during the early stages. And of course, this study is not completed because we need to further investigate into changing the beam currents, because for all these simulations here, beam currents was set to 40 milliamps. And also the voltage configuration is essential to see how the system behaves and its limitations, like how far can it be pushed. And thank you for your attention. That's all for me.
Hello, everybody. It's Nada Ustadic, and I also study physics at University of Sarajevo. This summer, I was a summer student at CERN for 8 weeks, and I'm going to briefly tell you about work I did there. So I worked on LINAC-3's ion source, which is electron cyclotron resonance ion source, also known as ECR. And LINAC-3 is starting point in the heavy ion production when it comes to experiments at CERN and LHC. So ECR has a wide range of application in industry and medicine because of the stability of the beams it produces. And the working principle is that free electrons are injected in the plasma chamber, and simultaneously microwaves that are produced by our accelerator are injected, and plasma is ignited once resonance is reached. Then plasma needs to be confined using in a so-called magnetic bottle, which is created using solenoids. Solenoids create axial field, and hexapoles, which create radial field. So once the plasma is ignited and confined, the beam needs to be extracted using set of electrodes. And after that, it goes to through dipole magnets and Faraday cup, which are used to scan the charge state distribution. And optical emission spectra is recorded in the chamber itself. So my work was mostly experimental. My task was to obtain spectroscopical data and charge state distribution. So spectroscopy has been recently implemented, and it's non-invasive diagnostic method, which is used to detect instabilities, impurities in cell source itself. And it's also used to detect what elements are present in the plasma chamber. So once the spectra is observed, background needs to be measured as well, and then extracted. And then we can proceed with detection of the elements. And I used NIST database to identify the elements. And because at the time I was there, the source worked on lead, so lead was detected, as well as oxygen, because oxygen was used as buffer gas. Well, because it's relatively new method, I needed to change parameters to see what are the optimal parameters to detect lead. So that's something I did as well. And then also, I needed to see if there's a correlation between optical emission spectra results and charge state distribution. Charge state distribution is also one of the most important parameters of the source. And it is invasive, and ions are separated based on the difference in magnetic rigidity. And also it sends the results when beam is extracted. So that's why it's important to compare charge state distribution scans and optical emission spectra. So this is just one example of detection of the elements present in the CSD scan. And once we have results, I try to find correlation, but I was at CERN for quite short time. So there were indications of the correlations between, so on the right side, we can see optical emission spectra, and on the left side, we can see charge state distribution. So there, if we notice increase under the area under certain peak, that increase is noticed in optical emission spectra. But this is something that needs to be more confirmed because I was there for quite a short time. And I would like to thank you all for attention. That's it from me.
Okay, hello everyone. My name is Medina Duganic and I'm a physics student at University of Sarajevo, and together with Danis and Naida, I was one of the summer students at CERN this summer. My project was also at LINAC 3 and sort of leans on Naida's project because we work together. However, my part was more computational than hers. Okay. So the main idea of my project was to make a code that will process the raw data from the source in real time, and then store the process data on the server and visualize the process data in CERN's Timber. There was already existing code in MATLAB, and my task was to convert it to Python. Why was this idea like taken into consideration is because I had to be able to track the data in real time. As Naida previously said, this is the only diagnostic for the plasma dynamics. This was, I'm not sure if you are able to see well, I hope you are. This was the intended workflow of my project. The idea was to make the code, then transfer the process data to the local CERN server, and then visualize the process data to Timber. This is how the raw data file looks like. It was given in the form of a text file, and my task was to find the areas under the peaks that were given. The main task of my project was to make a code. This is one of the specs of the code that I needed to make. Okay, this is how the peaks are visualized. Okay, so this is also not sure if you're able to see, but I will say what it says. So this is how the output file of my program looked like. It gives us the it gives us the file name of the output file, and then it gives us the timestamps as well as the areas under the peaks and the wavelength of the peaks. As Naida said, we worked with LED, so this is the element that I was looking for. Okay, so about the second part of the project was the technical aspect of how to transfer that data through servers and store them in CERN's local servers and then visualize them. However, what we realized during the project was during the time and with my credentials that I had at the time, I wasn't able to do everything in the span of 2 months. So somewhere between after I finished making my program, I had to kind of stop doing my project and leave it to somebody else. But we managed to find all the ways how to do it. And it was kind of sort of transferred to be done later. And yeah, so just to reiterate one more time, the main goal of the project was to make the program that will process the obtained data and integrate it with CERN's server and then visualize it with CERN's Timber. That's it. Thank you for your attention.
Wonderful. Any questions for any of the students?
I just want to say that I feel very proud seeing this work, and I would like to point out that they are supported by the Three Physicists Foundation, but they are here because they applied for funds. They knocked about 20 doors, and they got their travel funded here by a company. So congratulations. And I really hope that our generation will be able to put a facility, a research facility on the ground so that these young scientists that we are training, they have something to come back to the region. Congratulations.
Thank you very much.